Guess what time it is? Dynamics time! Rawr! Okay, I hope you're all awake now. Should I shout louder into the microphone? Okay, I'm losing it. Sorry. Welcome back to your favorite class. 3 o'clock. Time to go. Announcements. Number one, obviously simulation due tomorrow, Friday. Most of you have turned it in already. Asked questions about it in office hours. So good job getting a head start on it. Seems like a lot of you like those MATLAB assignments, so that's good. A little bit different flavor for the class. So if you've done it, hopefully you've enjoyed it. And if you have yet to do it, get going, baby. It's almost time. 24 hours. Better move. All right. Announcement number 2. Homework number 4 posted. It's on work and energy. After today, you should probably be able to tackle it. Okay, we're going to finish up our notes today and work through an example problem. So hopefully after today, you'll have some tools to execute. All right. Lastly, and sort of in the future, 1 week from tomorrow is your second exam for the class. So that'll take place during the normal lecture time, and it'll proceed much like the previous exam went. So, have your laptop pointed at the direction of your work, 50 minutes to do the test, scan it in or take a picture, send it to me when you're done, and that's how that's going to go. So a little bit more detail on that coming, but going to be 3 problems just like the last test, 1 on kinetics, 1 on work and energy, which we're talking about now, and 1 on impulse and momentum, which we're doing at the very beginning of next week. So that's what we got going on for the class. Any questions on any of that stuff? Okay. Well, if there's no questions, and it doesn't look like there are, then I will move you guys over to the white pad and we'll finish up the lecture notes for work and energy methods and hopefully make our way through an example problem today. All right, so work and energy, here we go. Kind of capping off the discussion today on work and energy methods. So remember that the equation that is governing all of this stuff that we're talking about for work and energy is conservation of energy. Which is T1 plus V1 plus U1 to 2 equals T2 plus V2. What we've been doing this entire week is upgrading your knowledge of what is the various components that make up this equation from sort of the particle forms of them to the rigid body dynamics forms. So what is T1 for a rigid body? What is V1 for rigid body? So on and so on and so on. All right. We started with our definition of work of external forces and moments, this U1 to 2. We're kind of finished up our discussion about the kinetic energies yesterday, so T1 and T2. And today we will put a cap on this and discuss these potential energy terms, V1 and V2. So work of external forces. And moments was this sort of U1 to 2, which in big boy form was moving from position A1 to A2 of the forces dotted into the path that they move, plus work associated with moments as they act on our angular motion from angular position A1 to A2 of m dot d theta. And with our example problem a little bit later, we'll see how this equation actually applies. So that was the big boy form. We had sort of a simplified form for when we wanted to look at 2-dimensional Cartesian dynamics, which is mostly like what we're doing in this particular class. All right. So that was your U1 to 2, and this is sort of like the 3-dimensional form. All right. We also looked at kinetic energy, which was this T variable, and said that the kinetic energy of a rigid body was equal to 1/2 the mass of the rigid body multiplied by the velocity, the center of gravity of that rigid body squared, plus the kinetic energy associated with angular motion, which is 1/2 Ig, which is the mass moment of inertia of an object about its center of gravity, multiplied by the angular velocity of that particular object squared. So this was your dollar store version. that we're going to use in this particular class. So this is the 2D form. And we had the more mathematical form, which if you're going to sort of use an arbitrary coordinate system or maybe do some more advanced mathematics later, this larger form is using the dot product, the velocity of the center of gravity of this object dotted with the velocity of the center of gravity of the object plus 1/2 mass moment of this object. Here, this would be a tensor. Not going to get into that too much, of omega dotted with omega. So this is your big boy mathy version that we sort of used in our derivation and whittled it down into the 2D version, right? So this is your 3D version. We're mostly going to stick with this equation here. But the point is that we had some kinetic energy associated with linear motion. So this is kinetic energy of linear motion. And this guy here is the kinetic energy of angular motion. So that was your external forces and moments portion of the work and energy equation. And we also had the kinetic energy portion, which we've sort of been whittling down over the last day and a half. Now, we move on to what is the easiest component. And it should maybe only take us about 10 or so minutes to get through. And that is the potential energy term. So this is the last term, and that is the potential energy term. Usually given with the capital letter V. And that can be a little bit complicated because we use V for velocity and V for potential energy. So I'll try to be like very clear as I'm moving through, like as best I can, what variable I'm sort of talking about. So here, this is potential energy term, this capital V. Now, potential energy has a variety of forms, and it can come from a variety of places. All right, so can come from many sources. The sources that you probably saw in your particle dynamics class were potential energy that might come from gravity. So this would be gravitational potential energy, usually given by something like capital V with a lowercase g, so V sub g. You may have elastic potential energy, usually given by the variable capital V lowercase e. And these are the two that you're probably most familiar with from your particle class. So you talk about elastic potential energy of a spring, for instance, and gravitational potential energy being something like the weight of the object multiplied by the height of the object above some datum, which we'll talk about a little bit more. But it can also come from other sources, right? So some other sources that are a little bit more hidden that you might not see all the time are like electric potential energy. So if you've got a voltage difference between two different locations and some charged rigid body or some charged particle, it's going to be drawn one direction or another, and this potential we call electrical potential energy. And hopefully you've talked about electrical potential energy in your physics class. So when you took physics 2, you talked about electrical potential energy. No variable, because we're not really going to talk about it in this class. But another source of potential energy that you might also have is chemical potential energy. So think about your car. You've got gallons of gasoline in your car that could potentially turn into kinetic energy. So we're feeding this liquid gasoline chemical into our engines, and there's some reaction happening that's turning that into a kinetic energy. Okay, so there is stored potential energy inside of the liquid that is gasoline inside of your car. So chemical potential energy. All right, same thing with, a bomb. Okay, there's chemicals in there that can explode and turn into potential energy, right? So a lot of different types of chemical potential energy. But just like in your particle class, we're really only going to talk about the first two here, and that is the gravitational potential energy with the variable Vg and the elastic potential energy with the variable V sub e. So this is mostly what we're going to talk about in this particular class, though I just want you to be aware that there are some possible other sources of energy that exist out in the world, including electrical and chemical and others. All right, so in this class, our potential energy just boils down to potential energy from gravity plus potential energy from some sort of elasticity. So let's talk about each one of these individual terms quickly, and we'll be on with it. First, let's talk about the elastic potential energy, which is VE. All right, elastic potential energy. If you've taken ME2004, or are currently taking it, or you've taken ME3005, which is this mechanics of materials sequence, then you know that objects that are able to be deformed by forces will store some amount of elastic energy. Okay. In this particular class, we're assuming that all of the bodies that we have are rigid, meaning that I can apply forces to our object and it won't deform in any way. Now, realistically speaking, that's not true, but that's sort of the assumption that we make in this class. So I'll just say here that in this class, our bodies are rigid. So no energy from deformation of the body. That's because all the bodies that we talk about in this class, we're going to be assuming sort of rigid behavior. So a lot of times when you hear things like elastic potential energy, people are talking about energy associated with putting like load on a structure, and it's sort of in this like condensed state that wants to sort of expand and release its energy. Okay. So we're not talking about that kind of elastic potential energy in this class. What we're talking about in this class is the elastic potential energy associated with springs. So in this class, we only talk about springs. All right. And I will tell you that the elastic potential energy associated with a particle displacing a spring or a rigid body displacing a spring is exactly the same. Okay. So pictorially, you might want to think about for a particle. You might have a particle here that's of mass m connected to a spring, which is, I don't know, hooked into some wall, let's say. And it has some original length, L naught. Right. Sometime later, let's say we pull this mass out some distance so that the spring is extended to some final position, which is LF, the final position. All right. And that means that we have pulled this mass out what we would call some distance x. All right. Well, in your particle dynamics class, you should have learned that the energy associated with this particular motion, or the potential energy that the spring has when it's displaced away from its original location x, is VE is 1/2 kx squared, where k is the spring constant and x is equal to the total displacement of the spring from its original position. So that is LF minus L0. All right, so that is your elastic potential energy of a spring. Now, whether that spring has extended because of particle motion or because of rigid body motion is irrelevant. The energy stored in that spring is the same regardless of what it's connected to. So we can draw the same exact picture, but now for a rigid body. It will look more or less exactly the same. Okay, here's your mechanics potato. It's got mass whatever you want it to be. It doesn't make any difference. We'll call it mass capital M. And let's say that this guy is attached to some spring here with some original length L0. And we'll assume sort of unstretched in this condition. Right? And our rigid body then sometime later gets displaced out to here. It's still connected in that same general location. All right, and it's now moved out to another position, which is LF here. And it's moved out away from its original location X. It's the same exact situation, except it's just attached to a rigid body except a particle. So it has zero bearing on what the spring is attached to, how much energy is associated with that spring. So we have the exact same general equation. So same result. That the elastic potential energy here is still 1/2 kx squared. Same exact thing. All right. So whether it's attached to a particle or a rigid body, irrelevant. All right. The energy associated with that displacement of that spring, 1/2 kx squared. So that's the elastic potential energy. That bit's pretty easy. Also easy is gravitational potential energy. Which is given by V sub G. Again, this sort of requires a series of pictures. Sorry if you're kind of still copying from up there. This again requires some pictures, potentially. Get that? Potentially? Okay. If I've got a particle that's up here, it wants to move downward. It has the potential to turn into kinetic energy as it's standing up here. If I were to release it, it would fall onto the table because that would be a lower energy configuration for that particle because it's closer to the center of mass of the Earth. So generally, we say that the potential energy that an object has requires us to define some location where that gravitational potential energy is 0. So this requires a datum where Vg is 0. Because this gravitational potential energy can exist basically at any location, we have to define some arbitrary reference point where that energy associated with that potential is 0. We typically do this by saying that, all right, some particle of mass m exists in some location here, and there exists some horizontal plane that exists that is a datum for which the gravitational potential energy is equal to 0. If that is the case, then the energy associated with the particle in this current configuration, which is at a height above that datum of h, you should have learned in your particle dynamics class, is Vg is the mass of this object times the acceleration due to gravity, g, multiplied by the height that that object is above that particular datum. So this is the particle dynamics version of the gravitational potential energy. It is more or less, again, the same for a rigid body. So this is a particle. And we have basically the same thing for a rigid body. And that is, if your rigid body here is mechanics potato, and it's got some center of gravity here, g, and this entire thing has a mass of capital H, well then the potential energy of this entire body on average is the potential energy associated with all of the mass of that rigid body contained at the center of gravity at a height h above the datum. So if we again have another datum, just here, and the center of gravity here is at position h, then again, the gravitational potential energy of this rigid body is, I'll say cap m, which is the total mass of the rigid body, multiplied by the constant of gravity, multiplied by the height that this object is above that particular datum. So again, another very simplistic definition. Where here, capital M is total mass of the rigid body. So saving sort of the most simplistic terms, which are these potential energy terms for the very end, right? Did a whole rigmarole for kinetic energy. That was kind of complicated. Here, the potential energy, much more simplistic. All right, so all together, our conservation of energy. Is the following. Remember our equation, which you will probably be sick of. Here we have T1 plus V1 plus U1 to 2 is T2 plus V2. We would say here that each one of these terms is the following. Here, T obviously is kinetic energy. So we have the following. The Ti is the kinetic energy of the body in state I. So wherever that state happens to be, whether it's Wyoming or Georgia or Massachusetts, kinetic energy of the body in that particular state. Given by the equation, Ti is 1/2 m velocity to the center of gravity in state I squared plus 1/2 mass moment of inertia of the body about the center of gravity multiplied by the angular velocity of that object in state I squared. Right? Vi is the potential energy of the body in state I, and it is given generally by Vi is the gravitational potential energy of this object in state I plus the elastic potential energy of this object in state I, given by VGI and VEI, where VGI is the mass of the rigid body multiplied by the constant gravity times the height of the rigid body in state I away from the datum. That is specifically for the center of mass, the height of the center of mass, the object, and the elastic potential energy of this object in state I is 1/2 k, the spring constant, times xi squared, where xi is the final length of the spring minus the original or the unstretched length of the spring. And lastly is our term associated with external forces and moments, and that is U1 to 2 is work of external forces and moments, which was given by the equations U1 to 2 is integral from A1 to A2 F dot dr plus integral A1 A2, the moments dotted into the path of angular motion. All right. We got it all. We got it all. We're A+ material. We got it all. We got kinetic energy. We got potential energy. Oh, what potential we have. Okay. So that's that. That's kind of closing out the lecture notes for work and energy. On to an example. pivot you guys over to the PowerPoint slides now so that we can sort of copy an example down and we'll work our way through it. All right. This example is complicated, has a lot of stuff. So I'll give you a sec to copy down. I'll transfer over to my white pad as well and get the relevant information, and we'll make our way through it. Foot-pound second squared, my favorite unit ever. Okay. I'll toss you back over to the white pad, and I have all the information down here that you kind of need. So if you're kind of copying down the problem still, you can keep at it with the information I kind of have here on the pad. All right, so we've got this flywheel and block combination. Okay, so here's this flywheel. It's so fly. And here's the block. Okay, so they're attached together with this rope, kind of making this all one system together. Okay, so whatever force is inside of the rope there, that's not external to the system, that's internal to everything that's going on. So that's not technically an external force that we have to consider. We've got the weight of the block, 240 pounds, the velocity of the block in its original or initial configuration, so subscript 1, 6 feet per second downwards. We were given a mass moment of inertia of the flywheel and drum combination, which is, in my favorite English units, 10.5 foot-pounds second squared. Exactly. The moment that we have from friction, which opposes this motion during the entire time, is 60 foot-pounds. We'll get to that in just a second. We want to find the velocity of the block after 4 feet of travel downwards, right? So the block is going to move from this location that you see here. It's going to move down 4 feet until it gets to another location down here. All right, so the center of gravity of this particular block is going to be moving 4 feet. So let's give ourselves some information here and say that this distance here, 4 feet. This is kind of the important length for us as this block moves from position 1 to position 2. All right, so attacking this problem, we're going to use our conservation of energy equation. So we're going to have something like T1 plus V1 plus U1 to 2 equals T2 plus V2. These are kind of how all of these particular problems are going to start, with this general overarching equation. Once you get that on paper, then it's up to you to start like whittling those terms down with information that you have. So this is our general overarching equation. And once we identified that this is kind of the problem that we have, well, we need to identify what is state number 1 and state number 2. All right, well, state number 1, this is when the block is in its like higher configuration. All right, so I'll just say initial position. And I'll say the block is in its initial position. And state number 2. it'll be block down 4 feet. All right, so those are my two different states. If I want to sort of label them here on the figure, it would be like state number 1 is here, and state number 2 is here. All right, so there are kind of two different configurations for this particular problem. All right, so let's start whittling away at some of these terms. First, kinetic energy in position number 1. Whoa, I don't want red. Kinetic energy in position number 1. All right, well, since we have kind of two different objects in this system of objects, we're going to have to consider the kinetic energy associated with both of those objects. And they're kind of connected through this rope, so we sort of think of it as one whole system, but we can look at each of the individual components separately. So we're going to have some kinetic energy of the block plus some kinetic energy of the flywheel. And I'll just write T fly, because I'm just fly like that. All right, and this is all in configuration number 1. So each one of these two individual pieces has its own kinetic energy. So we might have something like 1/2 mass of the block and velocity of the center of gravity of the block squared plus 1/2 Ig of the block multiplied by the angular velocity of the block squared. So this is our general equation for the kinetic energy of a rigid body, some associated with linear motion, some associated with angular motion. We can also have a similar looking setup for the flywheel. All right, each one of these individual components could have both angular kinetic energy and linear kinetic energy. However, we can sort of see from our problem that the block is only moving in this linear sense, okay? The block itself is not rotating in any way. I mean, we're not told that it's like wound up on the string and then it's unwinding on the string or something, okay? So we're going to assume that this block has no angular velocity. And so this particular portion of the kinetic energy in the block is 0. There's no angular motion of the block, right? It's only moving up and down. In a sort of similar way, in position number 1, there is no linear motion of the flywheel, right? If we go back up to our position here, this flywheel isn't like moving this direction or whatever. I mean, the flywheel isn't going anywhere. It's pinned at A and it's fixed, all right? So by that same sort of regard, there's no motion of this flywheel in position number 1 either, right? So both those terms are going to be 0. The only things we're really going to be left with is energy associated with linear motion of the block and energy associated with angular velocity of the flywheel. So this will be 1/2 mass block times velocity at the center of gravity of the block squared plus 1/2 Ig of the flywheel times angular velocity of the flywheel squared. And this again is all in configuration number 1, right? So we have information for most of this. So let's get the information down here. So this will be 1/2 mass of the block. Well, we're given the weight of the block, so we can normalize the weight by gravity to get the mass. So we're told that this is 240 pounds. We're going to normalize by the acceleration of gravity in English units, which is 32.2 feet per second squared. So that is the mass of my block multiplied by the velocity at the center of gravity of my block in condition number 1, which we're told in the beginning of the problem is 6 feet per second downwards. So we'll say here this is 6 feet per second. You can write it as positive or negative. Doesn't really matter because it's about to get squared anyway, right? Now we add to this 1/2 the mass moment of inertia about the center of gravity of the flywheel given in the problem. 10.5, my favorite units, pound, foot, second squared, multiplied by the angular velocity of the flywheel in position number 1. We got a problem now because we don't know what the angular velocity of the flywheel is at this particular time. However, we can use kinematics to figure out what it is. So I'll say, need kinematics for the angular velocity of flywheel in condition number 1. Let's draw ourselves a picture. So we have this drum in the center of a flywheel, and hooked up to that at this particular location is a block that is traveling downward at a speed of 6 feet per second. Okay? We know that the velocity at this particular point on the wheel will be shared with the velocity that's at that particular velocity of the block. So that particular point on the flywheel has 6 feet per second of velocity downward, right? And we know, sort of by like the right-hand rule, that if we're at the center here and we know the distance between the center of the flywheel and the location where that velocity acts, let's call this r, which is the radius of sort of that inner drum, that there is a relationship between angular velocity and linear velocity, and that is that the velocity is the angular velocity of this drum, which we know is kind of obviously sort of going in this general direction, multiplied by the radius of this drum. Since they're sort of perpendicular to each other, we have this general relationship. So we can solve and figure out that the angular velocity of the flywheel has a general relationship to the block, which is the velocity of the block divided by the radius of the drum, r. This is sort of a kinematic relationship that we need to sort of continue with this particular problem. And so because of that, my angular velocity of the flywheel can be solved for in terms of the linear velocity of the block. So in this situation, after rearranging and plugging this in for omega, we have the velocity of the block, which we know is 6 feet per second, divided by the radius of the drum, which we were given up here in part of the problem as 1.25 feet. And don't forget, this guy gets squared. So we needed that sort of kinematic relationship between angular velocity and linear velocity to proceed with this problem. All right, so all values in this particular guy are known, and you can solve straight away, and have something like the kinetic energy of the flywheel block combination in position number 1 is going to be 134 plus 121 foot-pounds. Okay? This 134 coming from the block motion and 121 coming from the angular motion of the flywheel. All right, so they both have pretty equivalent contributions. So in the end, the total kinetic energy in position number 1 is 155 foot-pounds. Right? So we're done with our first term. Oh, man, I'm old. I'm tired. All right, so that's your kinetic energy in position number 1. Next, we got to talk about the potential energy in position number 1. All right? We don't have any springs in here. So if we wrote out our elastic energy in position 1 plus gravitational potential energy in position number 1, well, I mean, I don't see any springs in this thing. So there's no springs acting on this guy. So we don't have any elastic potential energy in any configuration. All right, so that guy goes to 0. Now, gravitational potential energy, we're going to have to define a datum at which position our gravitational potential energy is 0. So here I'll say we need a datum. To define our gravitational potential energy. So typically, you want to define a datum at the lowest position of interest in your system. That's because we typically want to define positive values for potential energy So if you set your datum as like the lowest point having zero potential energy, then all of your potential energy values are going to end up being positive, and it just makes your life a little bit easier when it comes to calculation. Okay, so for this particular problem, I'm going to say that because my block is sort of at its lowest point in configuration number 2, that I'll set my datum here. And this is where the gravitational potential energy is equal to 0. All right. So when the block is sort of in position number 2, it will have 0 gravitational potential energy. But that means in position number 1, it is at some height above where it will be, which is 4 feet away from the datum. So in position number 1, if I set my datum as like the bottom location, I'll have that my potential energy in position number 1 is the mass of the block times the acceleration due to gravity multiplied by the height that the block is above the datum in position number 1. All right, well, this term here, this is just the weight of the block, mg. So this will end up just being W times H1, and this is specifically for the block. So the potential energy in condition number 1 is the weight of the block, 240 pounds, multiplied by the height above the datum at which the block lies, which for us is 4 feet. So you work this out, and you'll end up with, here, the potential energy in position number 1 is 960 foot-pounds. How are we doing out there? Any questions? Ooh, I think I do have a question. What's my favorite scary movie? No, that's not the question. 225 foot-pounds. Oh, yeah, so I wrote 155. I'm sorry. Thank you. This isn't 155. Boy, math is hard. 255. Thank you, Hannah. Good catch. 134 plus 121. Oof. Tough. 255. Apologies. All right, continue. Now we got to get to a little bit of a complicated term, and that complicated term is the work associated as we move from position number 1 to position 2. So here we have U1 to 2. Our most general equation is going to be something like A1 to A2 of F dot dr plus the integral from angular position 1 to angular position 2 of M dot d theta. All right. We don't have any external forces that are acting to impede our motion or in the direction of our motion in this particular problem. So this first term here goes to 0. Unfortunately, I do have some external moments that are acting on the system coming from friction. So here I'll say we do have external moments from friction. Well, that's annoying, but we can deal. All right. So we're told way back at the beginning of this problem that there's friction that's opposing the motion, and it's a constant value of 60 foot-pounds. So what that means is generally this wheel is sort of trying to move in this sort of direction. All right, so my angular velocity is in this general direction. So the motion of that flywheel is going to be counterclockwise in direction. All right, so the general sort of positive sense. And so if I have friction that is acting to oppose that, well, that friction is going to happen right at this pin at A. And if my motion generally is in this direction, then the moment is going to act to oppose that motion in the opposite direction. So here the moment will act to oppose that general motion here in this direction. So this is the moment that is coming up from friction, right? So if we kind of do our simplified version, we'll have that U1 to 2 is equal to the integral from angular position theta 1 to angular position theta 2 of the moment here that's acting, which is 60 foot-pounds d theta. And because the friction is opposing the motion, It is in the opposite direction of the angular path that I'm traveling. So that frictional force or that frictional moment is going to be negative in direction. That's because my path is one way and the moment acts to oppose that direction. So if I dotted the vector of the moment with the path direction, that would be a sort of a negative dot product. All right. So 60 foot-pounds d theta. I got another problem. I don't know theta. All right. So what is theta 1? What is theta 2? I don't know. All right. As this flywheel sort of moves, it's going to move from, I don't know, some original position. Let's call it theta 1. And it's going to rotate around to some other position I don't necessarily know, which is theta 2. And I need to know what that angular displacement is so that I can include them as the bounds for this particular integral. So how am I going to figure that out? Well, fortunately, I know how far down this block has to travel. All right. I know that that block has to travel 4 feet in distance for this particular problem. I can relate the length of rope, which is 4 feet required for that block to move, to the amount of winding required on the outside of this particular drum in an angular fashion. Okay, so as my block moves down, it's going to force the drum to unwind in sort of a manner equivalent to the amount of rope that was required to move the block down. Okay, that general relationship is the relationship between the arc length and the linear length between a circle and the linear length. So if the linear length here is some amount ds, then the relationship between the arc length traveled and the angular path is simply given by the general equation ds is r d theta. So this is general arc length of a circle for the angular displacement that you traverse, right? So a relationship between angular displacement and linear displacement, all right? Now in this particular example, we know that ds is 4 feet. And we know that the radius of the drum where we're unwinding this arc length from is 1.25 feet. So that means that my total angular displacement moving from position 1 to position 2 is d theta, which is theta 2 minus theta 1, is just going to be 4 divided by 1.25, which is 3.2 radians. All right, hopefully we kind of all followed that general idea. So now I'm ready to punch that into my integral. Is that I'm going from random theta 1 to theta 2. Well, I can set theta 1 to be any arbitrary position as long as theta 2 is 3.2 radians beyond that. And here, my moment is constant over that entire path of 60 foot-pounds, integrating over d theta. All right. After integrating here, 60 times 3.2, retaining the negative sign, negative 192 foot-pounds. All right. So we've got U1 to 2. We've got our V1. And we've got our T1. Done with the left-hand side. Now let's go to the right-hand side, conservation of energy. V2, 0. I'm at the datum for my particular body, and I don't have any springs. All right. So in position number 2, this term here, since the object is at the datum in position number 2, the height of that object above the datum is 0, and so the potential energy associated with that object is just equal to 0. All right. Last thing we have to do is our kinetic energy in position number 2, which will look very similar to the kinetic energy in position number 1, except we have an unknown here, which is what we're solving for, which is the velocity of the block in position number 2. So here we'll have 1/2 mass of the block, velocity at the center of gravity of the block in position number 2 squared. plus 1/2 IG, which is the mass moment of inertia of the flywheel, multiplied by the angular velocity of the flywheel, which we know there's a relationship between linear velocity of the block and angular velocity of the flywheel, which is Vg of the block over the radius of the drum, r, all squared. All this information we have, the only thing we don't know is Vg. So we can retain Vg and understand here that after plugging in all the numbers, this will be something like 7.09 Vg block in position number 2 squared. And now we have everything. Sorry, I'm keeping an extra minute. Our equation here. Our T1 was 255. V1 was 960. The work from 1 to 2, negative 192, trying to slow this thing down, equal to T2, which was 7.09, velocity of the block in position number 2 squared, plus the potential energy in condition number 2, which is 0. Units here are foot pounds. So velocity will be in feet per second. You can solve for the velocity of the block in position number 2, 12 feet per second. All right. Kind of sped up there at the end, accelerated a little bit, but I think you guys all managed to follow that pretty well. All right, kept it 2 minutes. Apologies for that. I'll stick around for a little bit, but that's it for today. We'll do some more example problems tomorrow. Ta-ta.